we're going to look at graphing a polynomial function. And I want to look at this one. So this polynomial is already given to us in factored form. We can call it f of x, and we'll say f of x is equal to x times x plus 6 quantity squared times x squared minus x minus 12. And one thing that we'll notice is with the example we did in class, it wasn't in factored form, and there may be times where we can't factor it easily, so we'll have to start with our rational zeros theorem. And once we've used that, we'll have to use synthetic division to find zeros. Here, this one's a little bit nice because we know that if f of x is equal to 0, x equals 0, or x plus 6 equals 0, or x squared minus x minus 12 equals 0. So x equals 0, x equals negative 6, and then x squared minus x minus 12. We're looking for factors of negative 12 that add to negative 1. So we can factor this into x minus 4 times x plus 3 equals 0. And here we get x equals 4, or x equals negative 3. So those are our zeros. I know we said that we can start by finding symmetry in class, but it doesn't necessarily matter what order we start in. Since I've got our zeros, because we were able to factor this completely, let's go ahead and talk about the behavior at each of the zeros, and then we will look at symmetry in just a second. So at x equals 0, if we look here, the multiplicity of this is 1. X equals negative 6, so that was when x plus 6 was a 0, and the multiplicity here is 2. And then the multiplicity in x plus 3 and x plus 4 factors are 1. So remember, we discussed that if the multiplicity was odd, the graph would cross through the x-axis, and if the multiplicity was even, it would come down, touch the x-axis, and then bounce back up. So I just typically say it bounces. So we found zeros. We found the behavior at the zeros, if they bounced or crossed. Let's go back and check symmetry here. In order to do that, we need to look at f of negative x. So if we evaluate f at negative x, we have a negative x, we have negative x plus 6 squared, and then we have negative x quantity squared minus a negative x minus 12. If we start to simplify this negative x, we have a negative x plus 6 quantity squared, and then negative x quantity squared is just like an x squared plus an x minus a 12. Hopefully when you look at this, without even having to expand everything out, we can see that this is not going to be even. Right? If we play the matching game, we can see that we're going to get different terms on the inside when we square that out. We have different terms here. Not every term's off by a negative sign, so it really won't be odd. So our symmetry here is neither. And I will leave expanding that out for you to go and see. So, we've checked for symmetry. Unfortunately, we don't have any, so our graph is a little more challenging. We'll have to find a couple more points. We found our zeros and determined the behavior. And now I would like for us to go ahead and think about the end behavior of this function. Since our polynomial was mostly in factored form, determining the end behavior is a little bit different. So as we look at our function f of x, what we're going to have to do is think about the highest power of x and its coefficient. So we'd have x, when you look at x plus 6 quantity squared, this term, when you square that out, the highest power of x you get is x squared. And then when you look at this third term in parentheses, notice that you also would have an x squared. So if we were to multiply these together, you can add the exponents. 1 plus 2 plus 2 is 5. So it's a degree 5 polynomial. And the lead coefficient is 1. Which means the end behavior should be down, up. It should behave very similar to something like x cubed would. So we have one more thing to do before we can graph this. We have to find some other ordered pairs. And I would say that we should find some in between our zeros, and then on either side of the last zeros. So when we do this, you can find specific values by making an XY table. And my suggestion would be that we probably want to think about something like 10 or -7. I don't even know. Let's go with -7. If it'll let me do this. Sure. X, f of x. So let's look at -7, maybe -4, -1, because 0, and -3, and then let's maybe look at f of x, so it's 2. And we're going to compute those values. So I'm going to do this really quickly and write them out. Just pause this a second. Alright, if x is -7, when you plug in -7 throughout that entire thing, you get a y value of -308. If x is -4, you get a y value of -128. If x is -1, you get a y value of 250. If x is something like 2, you get a y value of -1,280. And we should probably look at something like if x is 5. If x is 5, we get a y value of 4,840. You can see that our y values are pretty large, so we're probably actually not going to scale our y-axis by 1 unit, but maybe by 100s. Okay, so the last thing that we're going to do is we're going to try and put this all together on a graph. Alright, so I got my grid up, and what I'm trying to do right now is I scaled the y-axis a little bit differently, so every 2 I went up by 300, and I probably would have only used every one I went up as 100, but I started to run out of space. So, as we look at this one, I'm going to start by plotting my zeros. We had x equals 0, x equals -6, x was equal to 4, and x was equal to -3. So my zeros are graphed. I don't have to find my y-intercept because when x is 0, that means that's our y-intercept as well. And then we had some other values. So we said things like if x was -7, we were just under 300, -308. If x was -4, we were at -128. Let me check this really quick. And that actually should make sense, because if x is -4, -128, that's maybe like right here, because we bounced off the x-axis at -6. So I'm going to connect these with a smooth curve, and should bounce, so that means it's going to come back down. When x is -1, I had a y value of 250, And that makes sense because at x equals 3 we said we were going to cross. At 0 we also would expect to cross because of multiplicity. So I'm going to go back down. When x was 2, we were way down here at negative 12,080. So I'm going to go down, and then we're going to have to go back up, and this will actually match everything we've done as well because we expect it to cross through when x is 4. Again, when x is 5, we're almost off the chart, so I'm just going to continue my arrow so that it points up. Notice that our end behavior is down, up. Notice that each of our zeros, at negative 6, we had a multiplicity of 2, so we bounced. At negative 3, we crossed. At 0, we crossed. And at 4, we crossed. There is no symmetry. We can see that just from looking at the graph we've drawn. And if we pick more points, we'll get a more accurate graph. But I'd say pick at least one point between each of your zeros. And if you go on to calculus, you learn other approaches on how you can get even better graphs.